Hi, Wheat North Geology students. Today we're going to talk about predicting earthquakes. Okay, so as we spoke about with the elastic rebound theory, is Earth's crust is elastic, right? So it builds up pressure over time, and eventually it releases all of that energy at once, which is what an earthquake is. So that Earth's crust is sliding, over the surface of the mantle, and when you get that deformation occurring at a plate boundary, either because they're sliding past each other in a strike-slip fault, right, due to that shear stress, right, at a transform boundary, or if you've got plates that are converging together, right, at those locations too, you're going to have different types of faults, normal faults and reverse faults forming, that ultimately result in earthquakes happening. So, in terms of trying to figure out when earthquakes occur, it's an important active area of research because people lose their lives and there's lots of money kind of tied up with the damage that's caused by earthquakes. And a lot of people live in earthquake-prone regions. Here in the Midwest, where we are, we don't really have a huge threat. In Southern Illinois, we're nearby, down by St. Louis. They have in the past had big earthquakes. But for us, we don't really worry about it up here versus like if you were out living in California or in some places in Europe or Southeast Asia. So we're trying to predict when these earthquakes will occur. So there's a few different hypotheses. One of them is that they're periodic, okay? And we're going to kind of look to see which one of these is really the most accurate. But the first one is that they're just periodic, and that means that the same amount of fault slip is separated by the same amount of time. So if you look at the graph here, we'll get out of the way. Along the left here in the y-axis is the cumulative fault slip. So this is how much as you go up. So it's saying, basically if you have a big earthquake, going on the x-axis here is the time. So a big earthquake, long time, earthquake, time, earthquake, time. Okay, so it's just saying we get earthquakes every so often as plates go around. The second hypothesis is earthquakes are time predictable. Okay, and what that's saying is the larger amount of the larger the earthquake is, or the larger the fault slip that occurs, the longer time it'll be until the next earthquake. So if you look at the graph here, it's this. If you have a big earthquake, right, with that big line right there, it's going to be a long period of time until the next earthquake. If you have a small earthquake, you're going to have a short period of time until the next earthquake. Okay, so that's what the hypothesis is for being time predictable. Now on that one too, you'll notice that we're hitting the red line here down at the bottom with those bottom points. Okay. Now on this one is earthquakes are slip predictable. So this is like the inverse of that, or the opposite. This one is saying is the longer the time is between earthquakes, the bigger the earthquake is going to be. Okay, so it's just kind of going the opposite direction. So look here, if I go a long period of time, it means I'm going to have a big earthquake. Okay, if it's a short period of time, it's going to be a small earthquake. Again, you'll notice here on this one, the top points are hitting the blue line. Okay. Hypothesis 4 is that earthquakes occur randomly and have random varying sizes. So we have variable time, variable intensity. So, it could be a long period of time with a smaller earthquake, and then it could be a short period of time, and then you have a big earthquake. So this one is saying it's just a little bit more random, and you'll notice on this one that none of the points are really hitting on the purple line, so they're not lining up at all. So it's non-linear, hence the concept that it's random. Okay. So the other day we looked at our quake casters, where you put the bricks on top of. We did this in class, where you put bricks on top of our little quake caster, and you made the bricks move and made observations about how they were moving around. And what you should have noticed with those bricks is that there shouldn't have been a real pattern to it, not a real discernible one that you could really figure out. Okay. Instead, what we find is that if we look at data and collect data, is that it ends up being, you'll notice that we're not lining. You've got a few that hit the line, right? But they're not landing on the line, which lends us to the idea that we have these variable wait times, and we have a variable size of the earthquake as well. So the conclusion here is that the data did not really match any of those three hypotheses. Really, the one that matches the best is that the earthquakes are relatively random. Okay, and as a result of that, it's very difficult for us to predict when the next earthquake will be. So if you watch the movie Geostorm, the scientists in there, they devise a way to predict when earthquakes will occur by measuring something with the magnetics in the earth, and that's, at this point, for us, is fiction. Okay, we're not there yet, but it is an area of active research. Okay, if you guys have any questions, obviously rewatch the video or stop me in class. Have a great day.